Then, good morning, everybody. Welcome to the Relativity course. The objective is to discuss really the very basics of general relativity. And we will also study some applications like black holes and gravitational waves and stuff like that. It is a subject of considerable difficulty, not really, but the very fact that it took Einstein 2 months to come up with special relativity and 10 years to come up with general relativity tells you something. So anyway, the plan is to start with a brief overview of special relativity. We'll do it today, maybe briefly tomorrow. And then I have this special treatment prepared for you is the first look at GR. So we will basically look at how far we can go without knowing any differential geometry and without understanding anything. And so we will see that actually we can predict lots of things just by doing hand waving and by using Einstein's ingenious idea of Einstein's elevator. And then, so we will develop some necessary geometric tools. I will tell you what manifolds are, what tensors are, and so on. And then we finally start discussing general relativity as we understand it now, and then we'll proceed to applications. So now I have in mind some advanced topics as well. However, I have no idea how much time we will have. So I'm worried that maybe none or maybe one lecture or something like that. So anyways, if time permits, I would like to discuss black hole thermodynamics because I think it's quite nice. And if even we have more time, we can either do rotating black holes or hidden symmetries, or how to understand general relativity from a special relativistic point of view as a self-interacting spin-to particle. So that would be also another possibility. So now if you want to read more, of course I encourage you to make your own notes, but I'll be putting on the SciWiki these Sci lecture notes. So far the text has, 50 pages, and it covers approximately half of the course. So another 50 pages hopefully will be written soon. There's many beautiful books on general relativity. They are not very inventive with the title, so typically it's called General Relativity or Introduction to General Relativity or something like that. But anyway, so the book which is appropriate for our level is the Sean Carroll's book, Spacetime and Geometry, and Introduction to General Relativity. But I think it's actually, I quite like that book, and it's like really easy to read, and it covers all necessary topics. Of course, there is a beautiful book by Landau and Lifshitz, Classical Theory of Fields. The part which we need is just about the gravitation part, which is about, 80 pages or something like that. Then there's a book by Z, Einstein Gravity in a Nutshell, and more experimentally oriented Hartel's book, Gravity and Introduction to Einstein's General Relativity. So he really proceeds like, I first need to understand, this experiment or this data. And so what do I need to do to understand this data? So it's really nicely written. More advanced books are Eric Parsons' Relativist Toolkit. It's really, really nice book, but it doesn't start from the very beginning. So it's like if you are taking second course in general relativity, it's a perfect book. But I'll be using some parts of this book. And there's a book by Thomas Ortin, Gravity and Strings. It's a very beautiful gravitational part, and then really crappy stringy part. And the reason is that the stringy part is just too concise. You cannot learn anything from the stringy part, but the relativity part actually is okay. So if you want advanced textbook on gravity, it's this book, and of course the standard Bible by Walt, General Relativity. All right, so you need to attend the tutorials, and you need to submit 3 homeworks on time, and you need to pass the interview to pass this course. Are there any questions so far? Okay, if not, so let me just jump into it. And chapter 1 is just the overview of special relativity. Overview of special relativity. And because we have the classical physics course or whatever, we can go through this very, very quickly. So part A will be spacetime and causal structure. Which is really the basic thing which you need to know about the spacetime. So when people start discussing special relativity, they typically start with Lorentz transformations and stuff like that. Well, they are just a secondary thing. What really is important is the causal structure. How, what is different in the space of Newton and what is different in space of Einstein. And this is not working. Interesting. Okay. So what is a spacetime? So spacetime is a continuous set composed of events. So it's a continuum composed of events, where event is simply something which you assign 4 labels. So it's something which happened at an instant of time, and you have the position in space. So events are points of space in an instant of time. And this is true in both, in special relativity as well as Newtonian physics. You know that I can also have a spacetime in Newtonian theory, but the spacetime is like very rigid. It really distinguishes the space from time. So in special relativity, it will be much more bound together. All right, and so the point that it's really what causal structure means is how you can travel in the spacetime. So suppose you have an event P, and then you have 3 distinct possibilities, one of which necessarily occurs. And so if you consider another event Q, and if it's possible to go from P to Q, so observer, and here I mean really a massive particle or somebody who obeys the physical laws. So observer can travel from P to Q. Then you say that Q is to the future. Then Q is to the future of P. Okay. Now, of course, that's one possibility. The other possibility that it's precisely the other way around. I have my P, and it's possible to travel from Q to P. Then you say that Q is to the past. So Q to P, and then Q is to the past of P. Right? So these are the 2 situations when actually the observer can see both events, right? So in principle, I can travel from Q to P, then Q is to the past, and if I can travel from P to Q, then Q is to the future. But there's also a third possibility of events, and that's I cannot do it. So there is no observer, no massive particle can actually see both events. And so that's also a third option. Third option is observer cannot see, cannot see both events, both P and Q. So no matter how fast he travels or whatever, he cannot reach both events at the same time. All right, so now having introduced these concepts, like to the past, to the future, what is future, what is past, and what is neither, we can distinguish now the Newtonian case and the Minkowski case. So in Newtonian case, so Newton, the space simply looks like you have a 3D surface of things which are simultaneous. So this is a 3D simultaneously surface. Okay. And this precisely forms this third option. So whatever the points on the surface, the observer can never see them, see two of them. So now whatever is is up as the time flows this way. So this is future, and whatever is at the bottom is the past. So I can travel arbitrarily fast from one point to another. That's why if I take just a little bit later surface here, so no matter where I am here, I can travel all the way down there because I simply have no limit on my speed of light or whatever. So everything which is really up of this 3D simultaneous surface is in the future, and I can reach it. A physical observer can reach this. All right. So now the situation is very, very different in the relativity, on special relativity or Minkowski scheme, where so here the crucial role is played by this simultaneity surface, and what is really, very important, it's a 3D surface. So this is really important. It's a 3D. So these are the events in 3. Events in 3. So these are the events which the observer cannot see, P and Q. So now this thing is much, much bigger in the Minkowski space. And the reason is that the basic structure is not that this 3D surface, but is that of the light cone. So if I have an event P here, then I simply draw a light cone here. And the statement is that the possibility 1 is that is to the future is what is inside the light cone. So it's here. So all the events which are inside this cone here form the future. All the events which are in the bottom one are the past. And now the events in the third option are much, much bigger. And so whatever is outside of the light cone is called space-like events. So now the option number 3 actually is a union of the space-like events, plus the light cone itself. It's simply what can travel at the speed of light, so stays on the light cone. So massless particles or whatever, they stay on the light cone, again on the light cone. And so physical observers can only go from past to future, but they cannot be on the light cone, or they cannot travel this way here. And so now you see that this is much bigger set than this one here. So here I simply had a 3-dimensional hypersurface. But here the space-like events themselves, they are already 4D set, right? So I can draw, well, this thing here will be one surface, but then I can draw another surface like this. Not really. And there'll be another 3D surface. So in the end, this is just 4D surface, so 4D set. And so it's much more restrictive. So this is a 4D set, not a 3D one. And so really the causal structure, the way how the physical observers can travel is much more restricted in special relativity than in the Newtonian case. All right, are there any questions so far? So now just a remark that the light cone, so this is the situation as it happens in special relativity, and so you have really global inertial frame, and you have this nice light cone which is true everywhere, so it's the same light cone everywhere. But the same structure will be true also in general relativity, but only locally. So light cone structure also important in general relativity. So locally, you still have the same light cone, but these light cones, if you look at them like from the global point of view, they can sort of twist around. Light cones. So general relativity locally, that's very important. Locally, but light cones can twist around. So what it means, so let's have an extreme example. Let's have an example of a black hole spacetime. So black hole. So I just draw the radio coordinate r here, and there'll be time here. So now you will learn in about 2 weeks from now that there's a special radius for the black hole, which is at r equal to r plus equals to 2m. So if you want a black hole of the mass m, and then this black hole is assigned a special radius r plus, which is 2 times that mass. So now if you are very, very far away from that black hole, and so what is underneath, so this is the horizon, and what is underneath the horizon is really called the black hole region, whatever. So black hole is whatever is here. So now if you are very, very far away from black hole, then, well, okay, so you still have sort of like a flat space there, and you still have that same thing. So the light cone looks as you would expect. So it's pointing upwards, and it looks exactly the same way. However, as you come closer to the horizon, the gravity becomes stronger. And so what it does is that the same light cone is basically preserved, but it's twisted now. It's actually, as you go here, sort of starts twisting this way. So if you are exactly on the horizon, then the light cone looks like this thing here. So now remember, light cone tells me how I can move, how the physical observers can move. If I am here, I know that I have to travel within the light cone to the future. So the same thing is true here. So if I am at this point on the horizon, then the only way I can travel is actually this way. So I have to be inside the light cone, which means my radius is decreasing. So actually, if I am on the horizon, there is no way I can escape from the black hole. In fact, I have to fall inside the black hole. So observer has to go inside. And if you are even closer to the origin, r equal to 0, then the light cone is even more twisted. So it looks like this. And so then you have to basically travel to the region where r equals to 0. As we will learn, that's the region of singularity. So there's a singularity here. That's where the Einstein's general relativity breaks down. Nobody knows how to deal with that. But anyway, it's a prediction of general relativity. General relativity predicts its own doom. Is that, yeah, so there are singularities where the basic assumptions actually break down. So anyway, so the light cone is still very, very important. The only thing is that it's only important locally. And so as I travel throughout the space-time, the light cone can sort of twist around, and it can change the structure. So locally, the causal structure is the same, but globally, it's not. Are there any questions to this? All right. So now we understand the difference between Newton and Minkowski and general relativity. So how to go from to the most general one. So now staying still within the realms of special relativity or Newtonian physics, you know that very important concept is that of inertial observers. So inertial observer plays important role in both Newtonian and special relativity. Newton and special relativity. So by the way, when you learn Newtonian physics in the high school, so then you learn this very, very, very strange first law, which doesn't make any sense. It's like if there is no force, there is zero acceleration. And then the second law, if there is a force, there is this acceleration, right? But then it's immediately obvious that whatever the first law told you immediately follows from the second law, right? If I have zero force, of course I have zero acceleration. It seems like going from second to first is a trivial step. But of course, this is not how you should be learning Newtonian physics. So the first law in Newtonian physics, what it's really how it should read is that there exists a special frame, which we call inertial frame. And in this special frame, the second law has very simple form. So that's the first law. So there exists a special frame. And of course, this special frame corresponds to the inertial observer. And then the second law tells you, in this special frame, I have this beautiful and simple law, F equals to ma. Okay, so that's how the Newtonian thing actually should go. But the problem, of course, is that if there is one inertial frame and one special frame, there immediately is infinite number of them. And they are connected with the old one by rotations and by translations, so by Galilean transformation. So inertial observer, in fact, there is infinite number of them, and they are connected with one with another, connected by Galilean and Poincare transformations. Okay, so very good. So if I get one, it's difficult to get one, but once you get one, it's really easy to get all of them, and so they are simply, there's infinite number of these, and so none of these observers, none of these initial observers, is actually a preferred observer, and all of them, they write the same F equal to ma law, and all of them will have the same special relativistic laws. Right. So now Galilean, what I mean is really rotations and space translations. Poincare transformations is boosts, and rotations and translations, space-time translations. Is there anybody who hasn't heard what a boost is? It's just a standard special Lorentz transformation where you say I'm moving with the velocity v in the x direction or whatever. So that these transformations are called boosts. So now both of these transformations are basically rotations, but they are not rotations in space necessarily, but they are rotations in space-time. So these are spatial rotations, and these are space and time rotations, but otherwise they are the same. And the only difference is that now with time you have this minus sign instead of the plus sign, so the transformation looks slightly different, right? But other than that, these are basically just rotations. All right, so let me write an example of a boost, and so that's whatever you start your special relativity with. So t prime is gamma times t minus bx over c squared. So this is how the observer O is related to the observer O prime, who is moving with the velocity v in the x direction. And then x prime is gamma times x minus vt. And this gamma factor is just 1 over 1 minus beta square root of that. And beta is just v over c. Okay? So this is an example of a boost, so example of a motion in the x direction. And of course, what we see is that the speed of light enters here. And we already know from the classical physics course that that's something which was predicted by Maxwell's theory. Once you predict that, you actually kill the whole Newtonian physics. And so you have to actually, so Maxwell's theory is not consistent with Newtonian physics by simply the fact that predicting the absolute speed c. And so this c really plays an important role in special relativity. All right. So now if you actually plot what this transformation is doing to your frame, so if I have the observer which uses coordinate t and x, so that's my observer O, and now I have an observer which uses t prime and x prime, then you just draw a 45 degrees line, and then you make the same angle on both sides. So this is the same angle here as this one. And so this is my t prime, and this is my x prime coordinates. Okay, and so what you see is that each observer in special relativity still assigns this simultaneity surface. But in Newtonian physics, the simultaneity surface is true for any observer. Right? This is simply a surface which exists no matter what your state of motion is. Right? So no matter how fast I'm moving, I still recognize that this one surface, this one 3D surface, is my simultaneity surface. And all the observers have the same time. However, here, you see that, well, for one observer, the simultaneity surface is t equal to 0, so it's this thing here. But for the other observer, it's t prime equals to 0, and it's this surface here. So we have now observer dependent, simultaneity surface. And of course, this, is really the biggest obstacle to understand special relativity. That's why people still have problems with special relativity, is that, here, well, what's happening now actually doesn't make any sense. It's an observer-dependent statement. So there is no now at Alpha Centauri, right? It simply, depends on how the observer is moving. So now nothing can be happening in Alpha Centauri because there is no now. And so that's the biggest difficulty in special relativity. Okay. So now, this may be a little bit puzzling. So if the coordinates sort of do not make any sense here, the t prime and x prime, so is there anything absolute which we can really assign? So what about absolute quantities regarding the space-time? So quantities, that means observer independent. Observer independent. Well, so if you look at Newton, every observer agrees on what it means now, and hence every observer actually agrees on what it means to the future or to the past. So if you say another event is actually related to my old event by some delta t, because time is absolute here, they have all the same simultaneity surface, then everybody will agree on that. Okay, so in Newton, one thing which is absolute is, and is observer independent, is delta t. So we have absolute time. But of course, everybody also agrees on how distant the thing, what is the length of the between the two events in the simultaneity surface. So what is the length? So another one is delta x magnitude, and that's what everybody agrees in Newton picture. In Minkowski, so special relativity, of course, you use this you lose this absolute time, and so you don't have that any longer, right? There's many simultaneity surfaces. Nobody agrees on what delta t actually means, but what remains is still one quantity, and the same is true actually for the distance. Obviously, I'm twisting the x and t axis, both of them. But there's still one quantity which everybody agrees on, and that's this space-time interval. There's a space-time interval, which is the absolute one. And so you can write it as delta s squared is equal to eta mu nu delta x mu delta x nu. Where x mu are now space-time coordinates. So x mu is ct and then x. And this eta mu nu is the Minkowski metric as you know it. So it's diagonal -1, 1, 1. Okay. So this is the Minkowski metric, and these are the space-time coordinates. So now this thing has the absolute meaning, and it's observer independent. So every observer will agree on what this number is for the two events. So I take two events in the space-time, calculate this number. Every observer, no matter how the observer is moving or rotating or whatever, they will agree on what this number is. All right. Are there any questions? So this is what is called the causal structure. And it's really, you sort of see that it goes beyond Lorentz transformations. It really simply tells you, what is possible and what is not in the space-time. How can I travel? Which events are connected by physical observers and which are not? Yes?
Is there an intuitive way of understanding how boosting a frame changes the coordinate system like this?
Say it again. So what?
Is there an intuitive way of understanding why this happens?
Oh, you can just plot it, right? So you see that, for example, in order to get this axis, so this is your transformation which you are using, and then you, for example, want to plot this axis here. So this axis is whatever you want to call t prime equal to 0, right? So then you want t prime equal to 0, and then you see that t equals to bx over c squared, and so I can plot, and then so t is linear in x, and it's given by v over c squared, and so that's how you plot this one. Similarly, this thing has x prime equal to 0, and then you would use this thing here. Yeah. Other questions? All right. So I would say really this is the most fundamental thing about the space-time itself, is the causal structure. Now let me do what other people do, and that's the Lorentz transformations really quickly. And I just want to remark on 2 points. So Lorentz transformations are simply the transformations that leave the space-time interval here invariant. Leave space-time interval invariant. So that's a definition if you want. You will see that there is actually, apart from Lorentz transformations, there is also space-time translations, but let's forget about that at this point. So let's just have Lorentz transformations just leave the space-time interval invariant. And then you can easily show, and I don't know if you will show it in one of the tutorials maybe, that the transformation has to be linear and has to satisfy some nice property. So if I have my new coordinate system, x prime mu, then it's simply given by a linear transformation, lambda mu nu, x nu, where this lambda mu nu is a constant matrix, and it satisfies the property eta alpha b, basically leaves the Minkowski metric invariant, lambda mu alpha, lambda nu beta, eta mu nu. Okay, so this is what is called a Lorentz transformation. It's really the consequence of the fact that I want to preserve my space-time interval. So now notice that this is basically just something like lambda transpose times lambda. And if I raise the indices, I will have 1 equals to lambda lambda t. So it's something like 1 is equal to OOT or whatever. So which is a definition of a rotation or whatever. So if you were, so this is an analog of rotation, but now in space-time instead of space. So really, you see that the Lorentz transformations are rotations in space-time. All right. So now we can write down the inverse as well. As I said last time, if you have linear transformation, it's very likely that it will have inverse because it's typically non-singular. And so I can have an inverse where I put a tilde on this, lambda mu nu x nu. And so that this is inverse, that is lambda tilde, and lambda have to give you 1. So let's write it. Lambda mu nu kappa delta mu kappa, something like that. All right, so this matrix is simply inverse to that matrix here.
Sorry, is that an x prime nu?
Yes. Thank you. X prime nu. It's just an inverse of that thing. Other typos? Okay, and so as I said last time, basically, whatever transforms according to lambda, you call that object a special object. It's either vector or covector, and whatever transforms according to lambda tilde is the other way around. So now you define a vector, something that transforms according to lambda. So you will have v mu prime. It's an object which has this index mu, lambda mu nu, v nu, and then another object which has index down, omega mu prime, transforms according to lambda tilde, and it's lambda tilde nu mu omega nu. So this is a covector, and then you have a general tensor which transforms as, if it has some indices like this, it transforms according to lambda. If it has some indices like that, so tensor is basically like a product of vectors and covectors. And then you have a scalar which doesn't transform at all. So scalar, simply phi of x is phi of x prime. It preserves the value in new coordinates, the same value as it was in the old coordinates. Questions to this? So if we have seen this already in the previous course, it should be really simple. So now let me just give you an example of what these lambdas are, and to see really that we have rotations in both cases. So a simple examples. So we would have a rotation here, and for that lambda alpha beta. So this would be rotation around in the xy plane. So rotation in x, y plane. And then, so you have your coordinates. The first one is the time coordinate. So you have time here, and then you have x, y, and z. X, y, and z. So now nothing is happening in the time direction, so it's 1. But in x and y plane, you will have the standard rotation matrix cosine theta, sine theta, sine theta, sine theta, 0. So there's 0, 0, 0, 0, 0, 0, minus sine theta, cosine theta, 0, 0, 0, 1. Okay, so this is how your rotation matrix lambda, well, how your Lorentz transformation would look like if you wanted to have a rotation. And all it does, it takes the xy plane, y and x, by angle theta. So this will be my new y prime, will be my new x prime, and that will be angle theta. This just changes the spatial part. Okay. So now we have seen already the boost as well. And again, in the x direction. And so now you have, again, the rotation. However, you have the screwed up minus sign. Okay, and so actually causes, the minus sign causes that some of these things actually imaginary. So you have, instead of cosine, you will have cosine h. Instead of sine, you will have sine h. And then some slightly different signs. So it will be cosine h, theta, and there will be minus sine h, theta. And so this is t and x. And then y and z will be 0 and 0. And then it will be minus sine h theta, and then cosine h theta. 0, 0, that will be 1, 1, 0. Okay, so this is the boost. And you see it's really a rotation, except that it has the h in it. So of course, this is a boost in the x direction and should coincide with whatever we called boost in the x direction previously. So it should give me that transformation over there. And the statement is that it does, as long as you identify your angle theta properly with the velocity. And how you do it is that you call this beta, which is v over c. You identify with tangent h. And then doing some trigonometry, you find that cosine h theta is precisely given by your Lorentz factor gamma, and sine h theta is beta gamma. Theta is beta gamma. And so once you know that, you can just do the transformation on the coordinate and then compare with whatever you see over there for the boost, and you'll see this exactly the same thing. I just really want to stress here that you can write it in terms of this angle theta, and then it looks like a rotation, almost a rotation. Questions? Everybody's bored, that's good. So now I would like to discuss two phenomena which are interesting, and people really make big deal about them, and that's the Lorentz contraction and time dilatation. Of course, they are a direct consequence of your boost transformation, but let me just draw some picture to show you that it must be so. And then the derivation itself is just using that transformation there. But these two phenomena actually have far-reaching consequences, as we will see. So, okay, so let me just concentrate on this boost. And then we have the Lorentz invariant interval. So let me consider, so this is my thing, and I have my point P, which is at 0. And let me just draw, so this is time t, and this is my space x. And let me just draw a set of points which have the invariant Lorentz interval with respect to this point P. Okay, so first of all, I know that all the events which stay on the light cone have simply the interval equal to 0. Okay, so whatever is on the light cone, so the line x equals to ct has delta s square equals to 0. So all the points, so if no matter where I end here, I take this interval or that interval or that interval, all these intervals have 0 length with respect to this Minkowski metric. And similarly here. So all these points with respect to point P will have delta s square equal to 0. So however, what is this delta s square? So it's eta mu nu delta x mu delta x nu. But eta mu nu has this -1 +1 +1 +1. So what this really is minus c square delta t square plus delta xi delta xi. So I have minus here and plus over there. Now I require this is equal to a constant. So now if this constant is negative, what do you get? So let's say I fix this thing to be -1. What do I get? Yeah, I get a hyperbola. And so, for example, this thing here. So this is my hyperbola for which delta s square is negative. Another one, so there will be a delta s square equal to -1, and another value will be over here, or over here, or whatever, right? So but I have these hyperbolas here. So now if I have positive value equal to a constant, then I will have again a hyperbola, but now I'll be going more to the space. So I'll have this hyperbola here. So this thing has delta s square positive. Okay, so if you want, this line has delta s square equal to 0. This one has delta s square negative and more negative, and then this one has more and more positive. All right, everybody happy with this? So then let me just draw a direct consequence of this, and that's the time dilatation. So time dilatation. So what you want to know is, let's have one observer who has his clock, and this clock actually ticks, in regular times. So let's put this observer to be not moving. So then I have the frame t and x. Let the clock be at the position x equal to 0. And so all the clock does is it actually ticks in equal times. So this is my time t, and that's how the clock ticks. So this will be t, this will be t, this will be t, and whatever. So I'm placing the clock at x equal to 0, and this is what the observer sees. So now I have the other observer who is moving with respect to the first observer. And so he's boosted. And so he's using different axes. So he's using, again, this is the 45 degrees line. And then I have the axis phi prime. And then I have the axis x prime. So that's the other observer. This angle is the same. Supposed to be. Okay. So now let's see how this observer sees this clock, right? So now, of course, he measures the time clicks at the position. Well, okay, so this is the line of t prime constant, which is this one here. So these are parallel lines. So this is precisely how he associates t prime equal to constant line. And so he sees this time interval t prime. Okay, and then later on, you'll see another click, another parallel line, so they will intersect, and so will be another t prime here, and so on. Okay, so now the question is t prime bigger or is t bigger? So obviously from the picture, it looks like t prime is bigger than t. However, this may be misleading, right? So t prime may look bigger, but actually what really matters is how big the invariant interval is. That's something which is everybody agrees on, right? So what you have to do is that you have to plot the corresponding hyperbola, the corresponding thing which preserves the space-time interval. So now I am plotting this event, which is where the click is, and the corresponding hyperbola, which is this one here. And so this corresponding hyperbola has the same space-time interval. In other words, it has minus c squared t squared. So the same space-time interval, the same t prime would be this one here. Okay. But obviously, t prime, which is this thing here, is bigger than this point here, right? So we see that t prime is bigger than t, because this is what corresponds to t, right? This is what corresponds to t. So t prime, and so now I'll put this gamma, which is something which comes from the calculation, but you can immediately see from this picture that t prime is bigger than t, because this is how I preserve my length of the interval. So I only get here, but t prime goes all the way here. So t prime must be bigger than t. And so this is time dilatation. So what it means is that time for a moving observer goes more slowly. So here comes the first advice from special relativity. If you want to stay young, you better keep moving. So if you're moving fast, your time goes more slowly, and you have to. So time of moving observer goes more slowly. So the advice is keep moving. You'll see that you have lots of advices from special and general relativity. But this is really if you want to stay young, keep moving. Okay. So how to get this factor gamma is very simple. You just have to use the transformation. Yes?
My question is, what does it mean to draw the parallel lines and draw the lines?
So you agree that this line here is the line of t prime equal to 0, yeah. Right? So now if I want another, so you have to be using, so if you are using these coordinates, well, this is t equal to 0, this is t equal to 1, this is t equal to 2, t equal to 3, and so on, right? However, if you have twisted lines like that, what it actually means is that you have to draw again the parallel line. So this would be t equal to 1, this would be t equal to 2, t equal to 3. But now I'm building that, twisting that under 45 degrees.
No, I'm confused because when I'm comparing this t and this t, I'm taking the delta s is equal to constant line.
Delta s
lines be perpendicular to the axis, the time axis, not parallel to the x prime axis? Or is it simultaneous?
So this line, and what I'm saying is that this line here is simply the line of t prime equal to a constant. Right? Another line which is t prime equal to a constant will be again parallel line, but later on. Right? So if I want to know what my time prime was for this event, well, I have to observe it on a given time t prime. So I have to draw an axis which has t prime equal to a constant. So I have to connect this thing here, but I have to make it parallel to that one.
But when you were comparing t prime and t,
Yeah.
you draw a different line, right?
When I was comparing, you mean this one here?
Yeah.
Oh, so this one is just this hyperbola here, right? It's just this hyperbola here.
Yeah.
I just starting here, and I know that all these points here, they have the same space-time interval, right?
Yes.
Okay. So this space-time interval is the same as that space-time interval. Okay. But this space-time interval is precisely what the guy would call some time in my t prime direction. And that is smaller than the actual t prime. Think about it.
Because x is 0.
So then the idea of using this hyperbola is recalibrate our new axis, because we know how these new axes look like, but we don't know how the separation, what it means to pass 1 second in those new axes. So you just use the new parabola and then set x bar equal to 0 to find what t bar is going to be.
This thing here only tells you, what events have the same space-time interval. So now if I just make the axis like this, I call this new t prime, right? So this was my old t prime this was my old time for this observer, right? Then I will have the same distance here, but this is some time for an observer with this axis. Or if I have this thing here, this is some time for an observer with that axis, and stuff like that, right? And so they are all equal. They have the same value because this is the same space-time interval. Yeah. All right. So to confuse you even more. So by the way, this is very simple to derive from this formula here, right? So what you are doing is that you are measuring. So you placed your clock at x equal to 0. So you are just looking at t prime equals to gamma t minus vx over c squared, but x is equal to 0. You see that t prime is gamma t. Okay, and that's what's derived here. But this is like really nice, intuitive understanding the geometric picture of this. Okay, so another one is the Lorentz transformation, Lorentz contraction. So now what we want to do now is that we have a rod. So this is my observer t and x. And let's have a rod of length L in this frame. So I have a rod which has the constant length L here. And simply, this is my one end of the rod. I'm holding the rod here. This is x equal to 0, and this is x equal to L. And this rod simply stays there forever and sweeps the trajectory like this. So this is my trajectory of the rod. So each point simply moves in time. Okay. And so again, I want to know how this length is perceived by an observer who is moving. So again, I draw t prime and x prime. So obviously, the observer measures the length of the rod, let's say in t prime equal to 0. So this is the line, t prime equal to 0. So the observer measures this length, L prime. So now which one is bigger, L prime or L? So now this is why one has to be careful, right? Of course, L prime looks bigger than L, but it's not so, because if I now draw the line of constant interval L square, Okay, so this is my 45 degrees. So now the line will be this thing here, right? Is this part of the hyperbola? Okay, and so this distance here is L, right? So all the points here have the distance L to my origin. So this thing here is L, but I only measure this part of that. And so you see that L prime is actually smaller than L. And so if you do the calculation, L prime is L over gamma, which is smaller than L. Does it make sense? So in other words, if actually the objects are moving with respect to you, you see them contracted, and you see a smaller length of the object. So these are two predictions of special relativity, which are not very intuitive, but they have far-reaching consequences. So one of them is that you definitely heard about the cosmic rays hitting the Earth's atmosphere. As they hit, actually produce some muons in the top layers of the atmosphere. And so now these muons actually travel towards the Earth, but actually the distance is too big for them because they decay very quickly. So now if there were no contraction, Lorentz contraction, they would never make it to the surface of the Earth, but they do, and people observe them. Another way how to look at them is that actually look at the same problem, is that you say, well, actually, because they are moving, their time goes more slowly. And so if the decay rate of the muon is, I think, like 2 microseconds or something like that, they can actually live longer than that. And they can live something like 10 microseconds, which is precisely the time they need to reach the surface of the Earth. Stuff like that. So you know, these effects, of course, have been measured, and so you know, the cosmic rays and then you know, these muons is one very nice example where you can see either explain the phenomenon by time dilatation or by Lorentz contraction. Yes.
Just so I know, like, especially too for homework and stuff, do you make a distinction between the words see and observe in relativity? Because some people make a distinction between see and observe, because observe is like the relativistic effects, and see is like without the. Yeah,
that's right. That's right. It's two different things. Is, you know, one thing is, you know, what's really happening, and and the other thing is how the various observers see it. And you know, you can distinguish. Well, you should distinguish these two things, and you know, there will be different answers. Yeah. So by the way, now people, of course, especially because of you know, the fact that there is no these 3D surfaces of simultaneity, and that actually the time is relative, it makes, you know, lots of troubles for people. And so people keep inventing various paradoxes where you know, they try to show that special relativity is inconsistent and stuff like that. So I would just say, beware of paradoxes. But the answer is that, you know, no matter which paradox you invent, you can typically explain it by either special relativity, or actually, if the paradox goes beyond special relativity, by general relativity. So there is no contradictions in special or general relativity. So all these paradoxes can be solved. You will solve one famous paradox, twin paradox, in your tutorial. So you can sleep well. Special relativity and general relativity are consistent, and there are no real paradoxes there. Okay. Questions? All right. So now I think this was the most interesting part of the review of special relativity, especially the causal structure. But let me also review briefly this relativistic particle and the Maxwell theory. Hopefully this will be first of all, related to what we have done in the previous course, but maybe going a little bit beyond what we have done there, but not really too much. So take it as a repetition of what you already know. So part C will be relativistic particle.
I have a question.
Yep.
So the causal structure implies time dilatation and Lorentz contraction, that it's something that we measure and we can see. But do you know if we could have these phenomena without having a causal structure in spacetime?
Sorry, phenomena which would?
Time dilatation, for example.
Yeah.
Like if we could be measuring that and seeing that, like with this muons thing, and not necessarily having a causal structure in space.
You are saying, you are asking, are we really testing the causal structure or something like that?
Yeah.
I would say so.
Like no one has proven that time dilatation and Lorentz contraction imply like the causal structure we assume.
Well, people definitely observe these things, right? However, now a couple of years back, for example, people observe this superluminal neutrino in CERN or whatever, right? So now they said actually, you can violate the propagation of speed of light. Neutrino are massive, but they can still travel faster than the speed of light, and that millions of theories actually emerged in one day, and they were doomed the second day because actually there was a mistake in the data. So of course, yes, still you have to make sure that everything is consistent with the speed of light and whatever. There. Yeah, but so far is. Yeah. All right, so we have a relativistic particle. So the statement is a point-like object, sweeps a trajectory in space-time and you can parameterize it by a parameter lambda. So this is your t and x, and then the trajectory looks like this. And you can parameterize it by the parameter lambda. And it simply, it tells me, being like points on this thing, where the particle was in a given instant of time. And then the velocity is respect to the parameter is dx mu over d lambda. Of course, you require that this lambda parameter is nice. It doesn't go forward, backward, or whatever. That it's like monotonous function which keeps increasing along the curve as you sweep up the trajectory. And so, as we discussed in the previous course, you can now construct the time interval for these things. And you may be asking, is this actually bigger than 0 or equal 0 or smaller than 0? And then you say the trajectory is time-like, space-like, or null. Okay, so eta mu nu dx mu over d lambda dx nu over d lambda is either 0, and you say the trajectory is null there, or it's negative, and you say it's time-like, or it's positive, and then you say space-like. So now what I told you about the causal structure, so observer is associated with massive particles, which is the real physical particles, and the observer always travels within the light cone, so actually that corresponds to the time-like trajectory. So these are observers or massive particles. and this will be the light. So for a massive particle, it's always the trajectory is time-like at every point. So by the way, from what you see here, it's immediate to generalize this to more than point-like objects, right? So now you can imagine you have a string, you have a rod. So now this is just one endpoint, endpoint 1 here, and then you have another endpoint here, and that sweeps another trajectory. So there will be endpoint 2. And so whatever is in between is my string or whatever. And so you can immediately generalize this to higher dimensional objects. But then it's obvious that the trajectory, so now this you wouldn't call a trajectory, but you would call it like a world sheet or whatever. World sheet. And so now it's obvious that you need sort of like 2 parameters to describe this world sheet. I need to say where actually, if I have some middle trajectory here, I have to say which trajectory is it. So I have to have some parameter, let's call it sigma, which tells me which trajectory I am in. So let's say sigma 0 is one endpoint, sigma equal to 1 is the other endpoint, and something in between is this trajectory here. But I also have the parameter lambda, which tells me where on that trajectory I am in time. So now if you have, for example, 2D object, let's call it a string, and simply this is a relation which tells you how x mu looks like in terms of 2 parameters, lambda and sigma, because now I have to describe where on the string I am and at which time I am there, right? But otherwise, it's precisely the same thing. So now a p-dimensional object will be simply a map which maps p parameters to my spacetime coordinate. So p brain is simply x mu, let's call it now lambda 1, lambda 2, lambda p. Minus 1. So I want to call this, so the point particle will be like a 0 brane, it will be like 1 brane, so it's p minus 1. Okay, so that would be a multidimensional object propagating in my space-time. I just have to tell where on that object I am at a given time, and then how this propagates. All right, questions? All right, so now let me concentrate on these time-like massive trajectories, massive particles. And let me describe them a little bit more. So we have a massive particle. So we know that for massive particle, that quantity is always negative. So you can introduce a special parameter lambda, which you call proper time. So d tau, I have now 1 over c. I'll get rid of c, and I probably did already several times, but eventually in 2 lectures, I think. So dx mu, dx nu. So this is my space-time interval. It's negative. Square root is positive. So this is my proper time. So tau is the proper time. It's a special parameter which parameterizes thing. So now if you look at this definition here, it's a Lorentz scalar, doesn't have any indices. So this is really a scalar, which is important. This is a scalar. So basically, if you have a vector quantity, I don't know, and then you divide it by this thing here, it will still be a vector quantity because this is not screwing it up. And so that's how we will define things later on. But also, I can write this. So this is just describing my trajectory. And I can write it in terms of the lambda. So I can simply write dx mu over d lambda here, dx nu over d lambda, and then put d lambda here. Or I can write it in terms of lambda prime. And I'll have dx mu over d lambda prime, dx nu over d lambda prime, and d lambda prime. It's still the same thing. So this is not only Lorentz invariant, but it's also reparametrization invariant. This reparametrization invariant. So now if you remember the course, so what I will tell you in a minute is that the free particles actually move such a way that they maximize their proper time. So the action is really an integral over d tau, but that integral is reparametrization invariant. So what it immediately means is that you have diffeomorphism invariance in there, and then if you go to the Lagrange to the Hamiltonian picture, the Hamiltonian is 0, as we have seen in the previous course. So by the way, I can write it also in terms of the parameter t, which would be just on my coordinate. So namely, so for example, e.g. choosing lambda equals to the coordinate time t. And then you have d tau equals to 1 over c minus eta mu nu dx mu dt dx nu dt, square root of that. But x mu is just, ct and xi. Dt. And so this is equal to 1 over c. And so if I have mu equal to time and nu equal to time, this is just dt square over dt square, so c square. But I can cancel with this c. So this is square root of 1 minus dxi over dt square, 1 over c square, and then dt. Which is, so this is just v square over c square. But this is what I call 1 over gamma. So this is dt over gamma. The gamma is the Lorentz factor, which I introduced previously. So you see that the proper time is related to the coordinate time t by this Lorentz factor gamma. All right. So now again, the same things you have seen already. So for velocity for the particle is simply you define u mu equal to dx mu. Now with respect to the special parameter t tau. Of course, this is dx mu over dt, dt over d tau. So this is my definition of the for velocity, the tangent vector, but now with respect to the proper time parameter. There's dx mu over dt, dt over d tau, but I know that dt over d tau is gamma. So this is just gamma. And then dx mu over dt, well, it's c. And then the velocity as we know it. Does it make sense? Just using this relation here. So dt over d tau is gamma. And then dx mu over dt, x mu is just ct and xi, and this is what it is. And I'll just leave up to you to show that u square is equal to -1. Which is obvious from here. We have gamma square and then minus c square plus v square, and it's equal to -1. Okay, then we have for momentum. Okay, this will be a little bit more interesting. So again, we have massive particle, and this massive particle has some rest mass in the non-moving frame. So if I'm sitting on the particle, I measure some mass, and this mass is called rest mass. And then you define the form momentum p mu to be this rest mass times the velocity of the particle. Okay, so that's a definition. Rest mass, of course, because by definition a scalar. So scalar times vector is still a vector, so this is still a vector. All right, so now what it is this, I simply just have to multiply by m0 whatever I see here. So this is gamma, okay, it's gamma c m0 and then gamma m0 times v, right, just using this formula here. All right, so now what you would like this to be is that it is related somehow to your spatial momentum as you know it, right? So you would better call this, so if you call gamma m0 equals to m, then this is just mv, and it's just the normal momentum as you know it. Okay, so it's a definition if you want, or it's a reasonable definition. I don't know if you can really go beyond definition. Z is trying to pretend that he's actually deriving this thing. I think it's more like a definition. But anyway, so let's call like a normal mass of the particle. It depends on the velocity, and it makes sense to call m to be m0 times gamma. Okay, so once we have that, our form momentum p mu is c times m, and then p. Okay, this is how our form momentum looks like: c times m and p. Once I do this thing here, so now, of course, the most famous formula of special relativity, the most famous paper of Einstein, which some people even understand, is that E equals to mc squared. Right? It's telling you that if you have an object of mass m, it has actually a huge energy, which is given by mc squared. Okay, so now you can use the formula E equals to mc squared, which you will derive in a tutorial following Einstein's steps. So Einstein published this beautiful paper, 2-page paper in 1905 or something like that, no references, no nothing, where he derives E equals to mc squared by some, great experiment he designed and using the facts people knew at that time. And then it was still a little bit complicated. So now in the tutorial, you will discuss even simplified version of this, which he published in 1947, when he published his book on general relativity. So you will reproduce this result. So really, that's how much energy is stored in any mass m. Okay, so once we have that, so we can write, instead of m, we can write E over c squared. And so what's really written here is E over c and the momentum. So you can write the momentum for momentum in this way, and you see that the zeroth component of the momentum is related to the energy, whereas the spatial component of the momentum is related to the momentum as you know it. Okay, so now this is beautiful. But look at something even more beautiful. So now I can actually write p squared, which is p mu. I'm using the Minkowski metric, and it's simply minus c squared over c squared plus p vector square. Okay, So that's just squaring whatever I saw here. But of course, this thing here is Lorentz invariant. And I can write it in any frame I want. Right? So I can write it in particular in the frame where the particle is not moving. So if the particle is not moving, so here's the formula for the form momentum. If the particle is not moving, the velocity is 0. So that thing is gone. And gamma is equal to 1. So it's just c square m0 square. So this is equal to minus m0 square c square. And this is evaluated in the rest frame. And so you have the beautiful formula which you will be using in the QFT course all the time, is that the energy, just rearranging this relation here, you see that the energy is given by c times p square plus m0 square c square, square root of that. Okay, that's your formula for the energy which you'll be using in your QFT course. That's all you need in the QFT course, apart from the light cone. Okay. Very good. So we have this. So now, by the way, this was derived for massive particles, but the last formula is valid also for the massless particles. So now let me consider two cases. So case one, m0 is 0, so we have massless particle. And okay, so plugging m0 equal to 0 here, I immediately see that E equals to Cp. Which is a relation which was known from Maxwell theory for photons, that really the energy of a photon is somehow related to the momentum. But it's a really beautiful formula, valid for massless particles. On the other hand, if m0 is not equal to 0, then I can maybe expand for small velocities. And so you can write E equals to, we can take m0 c square out, and then you will have 1 plus p square over b over 2 over m0 c square. This is what it is. And now, assuming that the momentum, the kinetic momentum, is smaller than m0c, you can just expand this in the Taylor series. And so m0 c square plus p square over 2 m0 plus other terms. And so you see that the energy is actually given by the rest energy m0 c square. So this is like the rest mass energy. And this is the kinetic energy. And then you have the rest here. All right, so you see that this beautiful formula, of course, includes whatever you know, that the energy is p squared over 2m. However, there's this huge contribution due to the rest mass. And it's like a special case of this mc square formula, where this is really, when the particle is not.
One question. What is the plus minus sign in that equation from the square root?
Yeah, we will discuss that in QFT. Yeah, exactly. So yeah, so people believe, well, of course, was a huge confusion about these things, right? So nowadays people believe that all the energies are positive. But when Feynman started discussing these things, they had these antiparticles traveling backwards in time with negative energies or whatever. Dirac was this Dirac C thing, is where you actually create a hole by kicking out the particle, and that hole would have like a negative energy. But in QFT, all the energies are positive. That's the choice. All right, I have 1 minute, which is perfect. So this, whatever I discussed here, was valid for any massive particle, right? But of course, special particles are those which are not influenced by any force, which are the free particles. Okay, so the motion of free particle, and as I said, the action simply m0 c square d tau. This should have the correct units now. So this is like energy and time, so that's your action. And so what you are really trying to do is that you are trying to extremize the proper time of the thing. So the statement is the free particles move on such trajectories so that the trajectory extremizes or maximizes the proper time. And this will not be useful for anything, how to calculate it, unless you actually write it in terms of the other parameter than the proper time. And so then this is just an integral minus eta mu nu dx mu d lambda dx nu d lambda, square root of that, and then d lambda. And this is how you calculate it. So now you treat this as a Lagrangian. This is eta. So dropping out the factor, which of course is important for the unit purpose, but it doesn't really enter anything. So if you identify the Lagrangian to be just minus eta mu nu dx mu over d lambda dx nu over d lambda, square root of that. And then you write down the corresponding Euler-Lagrange equations. dl over dx nu minus d over d lambda, dl over d x nu dot equals to 0, where by dot I mean derivative with respect to lambda, and you write this, you arrive at the free motion. So you get this, and you did it in your tutorial. That's why I'm not doing it here. So provided there's a trick. So everybody is happy with this trick. So you first write it in terms of the general parameter lambda, and then you write down this equation in terms of the general parameter lambda. And then once you write the equation, you say, aha, but my equation looks ugly. And so I want this to look much nicer. And so I say, then I actually identify my lambda parameter with the proper time. And once you have the proper time, this is nothing else than just minus u square. U square is minus 1. So this is minus 1 is plus 1. So wherever you see a square root, just plug 1. And that simplifies your equation. Everybody's happy with this trick. So just read the tutorial from classical physics course. So you have lambda equal to tau, and then you have the equation that du nu over d tau equals to 0. And so that's the geodesic equation. Geodesic equation in flat space. And I'll return to this equation tomorrow briefly, and then we will start first look at general relativity. Questions, comments? All right. Well, thank you so much, and see you tomorrow.